Hi everyone, so today we're going to talk about vectors. So this is lesson 7 of kinematics. So we've already talked about vectors in class, but to remind you guys, vectors are a mathematical tool that are used to describe physical quantities that have both magnitude and direction. Don't forget magnitude, that means numerical value. So vectors have a numerical value and a direction. We can represent vectors graphically. We do that by drawing arrows. So a vector is represented by an arrow. The magnitude of the vector corresponds to the size of the arrow. So if it's a larger quantity for this vector, we're going to draw a longer arrow than we would of a small magnitude value. The direction corresponds to where the vector is pointing. So here we have an image of a vector. The magnitude is the size of this arrow, and the direction indicates the direction associated with the vector. Another point of terminology, we call this end the tail of the vector, and the pointy end the head of the vector. So I want you guys to take a moment and think which of the following quantities are vectors and which are scalars. I know a couple of these we haven't talked about, but give a best guess. Just to remind you guys, a scalar only has magnitude, while a vector has both magnitude and direction. So, in this case, in this list, the scalar quantities are mass, position, temperature, speed, and length. Right? So it doesn't make sense to have a mass of 5 kilograms north. Right? The north part doesn't make any sense. So those are scalar quantities. The vector quantities we have here are acceleration, velocity, displacement. Those we've all talked about in class already. And then we also have force, momentum, and torque. Though we haven't talked about these yet, I want you guys to start getting the idea in your head that these quantities are vectors. That will be important on the AP exam. When it comes to vectors, we will be adding vectors a lot in this class. And to add vectors, there's multiple methods of doing so. We're just going to talk about the tail-to-tip method. In this case, what you're going to do is redraw your vectors. So in physics and mathematics, you can redraw a vector. The vector is going to be identical to another vector if it has the same length and same direction. So as long as you draw it with the same length and same direction, the vector is going to have the same value. That is if they are the same quantity, right? So a velocity vector of 2 meters per second north is going to be the same as another velocity vector of 2 meters per second north. So you can't have an acceleration be equal to a velocity vector. Okay, so once you draw your vector, what you do is you redraw them so that the tail of one vector is touching the tip of another vector, which is actually we call the head of the other vector. But in this case, it's just called tail to tip because that's easier to remember. Once you redraw tail to tip, so here's our vector, and here's the other vector. We're adding these two together, and the resultant vector is going to extend from the tail of your first vector to the tip of your second vector. This vector here is called the resultant vector. It's the vector that results from adding your first two vectors. It's vector sum. It does not matter in what order you add the vectors. You're going to get the same resultant vector. So for example, in this case, we have vectors A and B. In this top portion here, we have added vector A to vector B. And then we get this resultant vector here that we draw from the tail to the tip. We could have very well have added vector B to vector A. And as you'll see, if you draw from tail to tip, you get the same vector. So it doesn't matter what order you add them. This method of the tail to tip method also holds true for adding vectors in a straight line. So here we have vector A and vector B. If we line them up tail to tip, so we would basically redraw this vector. We'll move it over a little bit over here. And if we redraw it from tail to tip, we'll see that we'll get a resultant vector that looks like this. We will also be using perpendicular vectors a lot in this class, and that's basically we're taking two vectors that are at a 90 degree angle with respect to each other, And when we add them together, it makes the resultant vector easy to calculate its magnitude and direction because we can use right triangles. So just to remind us that the Pythagorean theorem tells us that we can find the magnitude of this resultant vector, so the hypotenuse of our vector triangle, so to speak. We can use the Pythagorean theorem. A squared plus b squared equals c squared, where a, b, and c are the size of the vectors. And our trig functions are going to help us figure out the direction. In this case, it's going to be the angle of our resultant vector. So if you don't remember trig functions, you can remember them by this phrase SOHCAHTOA, where SO stands for sine is opposite of hypotenuse, CA being cosine is adjacent divided by hypotenuse, and tangent is opposite over adjacent. So if you don't remember those trig functions in particular, I have them listed here down below. And if you have trouble, please see me during lunch, and we can make sure that we understand the trig functions well. So it'd be best to see this through example. So here we're adding together two vectors. In this case, we have velocity vectors. We have a velocity vector that's 8 meters per second to the right. And we're going to add that to a velocity vector of 6 meters per second north, or up. Excuse me. So if we add them tail to tip, we redraw our 8 meters per second vector and our 6 meters per second vector here. And then we draw our resultant vector. So the vector we get when we add these two values together. So we can find the size of this vector by using the Pythagorean theorem. So we can take the square root of our 8 meters per second squared, and we add it to our 6 meters per second squared. Right? So let's just rearrange the Pythagorean theorem to solve for our hypotenuse. And in doing so, we get 10 meters per second as our result. The size of the magnitude of our resultant vector. Right? You can also use the trick that this is a 6, 8, 10 triangle. That's fine too. Secondly, we can calculate with what angle this hypotenuse, or this resultant vector, is angled at. You can use whatever trig function floats your boat or that you have enough information for. So in this case, I'm going to use the tangent function. So tangent of our angle is going to be equal to the ratio of the opposite leg divided by the adjacent leg. Right, so in that case, we're taking our 6 meters per second, dividing it by our 8 meters per second, and that leaves us with 3/4. The meters per second cancel out, which is good, because that's necessary for a ratio, in this case for a trigonometric function. So to find what the angle is, we just take the inverse tangent, or the arctangent, right, that's the same thing. So we take the arctangent of 3/4, and we get a value of about 37 degrees. So therefore, we can say that our resultant velocity vector is 10 meters per second at 37 degrees. This 37 degrees is with respect to the horizontal. We generally call, say, for example, the positive x-axis, that's going to be our 0 degrees, and we go around counterclockwise from that quadrant. So hopefully you remember that from math class. We are also going to very, very, very often be using component vectors. So in a sense, what this is doing is taking that adding of perpendicular vectors and reversing the process. So we're going to start with our resultant vector and break it down into the two perpendicular vectors that add to this resultant vector. We call these perpendicular vectors component vectors. So these component vectors are going to be labeled laying in our x and y direction. So it's best to see this by example. So here on the left we have vector A. Just as a note, whenever vectors are typed, they are generally symbolized with a bold font. So we have vector A here, which is at angle theta. So we can break it down into its component vectors by trying to draw our right triangle. So here we can draw a vector A sub x. So it's our vector A in our x direction, so the component in the x direction. So we're actually going to call this our x component of vector A. And that's pointing here to the right. And then we can have our y component of A pointing straight up. So here we've created our right triangle, with our resultant vector, the vector A, as our hypotenuse. We could have very well also drawn this triangle here on the right, where we have vector y going straight up, and the y component of vector A going straight up, and the x component going straight to the right. This is also valid. You just have to be careful because now the angle in our right triangle, this angle here is going to be 90 minus whatever this angle was. So just be careful with that. Whichever method you want to use, that's fine. Just be careful with your angles. So we can use trig again to solve for the length, or the size of these vectors, of these component vectors. So for example, if we wanted to find what the size of our y component vector, we can take the sine of this angle. So sine is opposite or hypotenuse. So the sine is going to be our y component divided by our a vector, our hypotenuse. That's what this expression here is showing. We can rearrange that and solve for a, and in doing so we see that our y component of vector a is going to be expressed as a sine theta. And we can do the same thing for cosine, and it's going to be a cosine theta again, similarly. If we're dealing with the other triangle that we drew, right, if we wanted to find, let's say we just tried seeing what sine of our angle would give us. So sine of our 90 minus whatever that angle is, we don't know what that is, we'll work in variable form. So sine of 90 minus theta is going to be our opposite, so our x component divided by our hypotenuse, that's vector A. So then if we rearrange solving for the x component, we can see that the size of vector A, or magnitude of vector A, is going to be the size of our hypotenuse multiplied by sine of 90 minus theta. You guys remember, hopefully, when you're dealing with trig functions, sine of 90 minus theta gives us a cosine theta. Right, those are equivalent. So if you notice, here, our expression for the x component was a cosine theta, and even dealing with our other triangle, we also get a cosine theta. And similarly, we can do the same thing for the y component, and we also see that they are the same expression. So it doesn't matter which method you use, you will get the same results, which is an important idea in physics. Finally, I have for you guys just an example. So here we have a velocity vector, and we want to break it down to its components. We'll be doing this a lot. We'll be given, say, an initial velocity at an angle, and we want to break it up into its component vectors so we can actually apply the kinematic equations. We'll talk about that in class. Alright, so in this situation, we have a ball being thrown at an angle of 150 degrees with respect to the horizontal, with an initial speed of 10 meters per second. So in this case, 150 degrees with respect to the horizontal is going to be measured counterclockwise. So we're going to have our vector be drawn in this direction here. And its initial speed is 10 meters per second, so that's saying that the magnitude or the length of this vector is 10 meters per second. The size of the vector is 10 meters per second. So we can use trig to figure out how much of that vector is going to be in our x direction, how much is in the y direction. So, for example, if we use the sine function, we'll see that the sine is opposite over hypotenuse. So that's our y component divided by our hypotenuse. If we rearrange that, we'll see that our initial velocity is v0 multiplied by the sine of theta. Plug in our numbers. Our initial speed, our initial velocity is 10 meters per second. Multiply that by the sine of 30. So I'm using this angle here, and it gives us 5 meters per second. We can, similarly, we can do that with the cosine function to find our x component. And the way I'm doing it with the angle of 30, I have to manually input this negative sign because I can see here that our x component is in the negative direction. You can, if you want, use an angle of 150 degrees in your calculations. If you do that, the negative sign out of this calculation here will fall out naturally out of the math because cosine of 150 is equal to negative cosine 30. So that's just something you need to worry about depending on what method you're using, but just be consistent and you'll be in good shape. Thank you.